Every Block Explorer website you've ever used, mempool, Blockstream, BlockCipher, is a pretty front end for the exact same data sitting on your own Bitcoin node right now. Right? When you query their servers, you trust them. When you open a terminal and type bitcoin-cli, you read data your machine independently verified against the consensus rules. Let me show you how to become your own block explorer. Let's start with the basics, connecting to your node. Bitcoin Core exposes an API through a protocol called a JSON-RPC, right? A standardized way to send commands and receive structured responses. Think of it as a language for talking to your node programmatically. The tool bitcoin-cli is your command line interface to the API. Type bitcoin-cli help and you see dozens of commands organized into categories: blockchain queries, wallet operations, network information, mining, and more. Every response comes back formatted as JSON, human readable, and machine parsable. This means the same interface that powers wallets, block explorers, and applications is available to you directly in a terminal. Your first commands should be health checks. Run getblockchaininfo. Your node returns its current chain, mainnet, testnet, or signet, along with the latest block height and verification progress. If progress reads below 1.0, your node is still syncing. Full sync validates over 1 billion transactions and can take more than a day. Next, run getnetworkinfo to confirm connections to the peer-to-peer network, the version running, how many peers you're connected to, which services your node supports. These two commands confirm your node is alive, synced, and connected. Now that we know our node is ready, let's look at what's inside the blockchain. Starting with blocks. Looking up a block requires 2 steps. Bitcoin Core indexes blocks by hash, not by height. So to find block 1000, first run getblockhash 1000. The node returns a 64-character hexadecimal string, the block's unique identifier. Getting the correct result here proves your node is synced past that height, running and responding to commands. Now feed that hash into getblock. The node returns the full block data as a JSON object. All header fields, the complete transaction list, and size measurements. This 2-step pattern, height to hash, hash to block data, is the fundamental lookup you'll use repeatedly. Let's apply it to a more interesting target. Run getblockhash 123456, take the returned hash, and pass it to getblock for a detailed field-by-field walkthrough. Block 123.456 returns a rich JSON object. Group the fields by what they tell you: identity, the hash, the height, and confirmations. How many blocks have been built on top, quantifying how expensive it would be to alter this record. Time, the timestamp set by the miner, and the median time from the previous 11 blocks. Miners can skew their timestamps, but the median resists manipulation, a deliberate design for an adversarial network. Size, total bytes, stripped size without witness data, and segwit weight units. Security, the Merkle rule. A single hash summarizing every transaction. Change one transaction and this hash changes completely, plus the nonce, difficulty, and cumulative chain work. Contents. An array of 13 transaction IDs. Blocks give us the big picture. The real story is in the transactions. Pick one of those 13 transaction IDs, run getrawtransaction with the transaction ID, a unique fingerprint derived from the transaction's contents. The node returns raw hexadecimal, the exact bytes as they exist on the blockchain, not human readable. Feed that hex into decoderawtransaction. Now you get structured JSON showing the transaction's full anatomy. On the input side, each input contains a field called txid pointing to a previous transaction, and a field called vault, the output index from that previous transaction being spent. And this is key. Inputs don't hold Bitcoin. They reference where the Bitcoin came from. On the output side, you see amounts and spending conditions. This transaction has two outputs, a classic pattern. Output 0 sends 0.015 BTC to the recipient. Its script pub key specifies who can spend it, and the type field reads witness v1 taproot. Output 1 sends 0.049 BTC back to the sender as change with type witness v0 key hash. Notice, the total inputs exceed the total outputs. That difference, never stated explicitly in the transaction data, is the mining fee. The miner who includes this transaction in a block claims it. Here's where it gets interesting. That TXID in the input is a breadcrumb. Let's follow it. Run getrawtransaction on that reference TXID, then decode it. You're now looking at the previous transaction, the one that created the output being spent. It has its own inputs, each pointing further back in time. Trace one more step, decode that transaction's input reference, your 3 transactions deep into history. Keep following, and this chain eventually terminates at something special. A coin-based transaction, the first transaction in every block, which creates new Bitcoin as the mining reward. It has no inputs referencing prior transactions because those coins didn't exist before. This is the fundamental insight. Bitcoin is not a balance in an account. It's a chain of signed ownership transfers, each independently verifiable, stretching back to the moment those coins were minted. One important caveat, a transaction ID is not permanent until confirmed in a block. Before confirmation, transaction malleability can alter the TXID. Even after confirmation, a blockchain reorganization could theoretically change it. But reorganizations become exponentially unlikely with each additional confirmation. 6 confirmations is the traditional threshold for high confidence. Here's what this all means in practice. The ability to query your own node means you never need to trust a third party to tell you what the blockchain says. Every balance, every transaction, every block, your machine verified it all independently against the consensus rules. This is the operational meaning of don't trust, verify. It's not a slogan, it's a concrete capability you now possess. And here's the practical payoff. Every Bitcoin wallet, every Block Explorer website, every Lightning node, every application built on Bitcoin, they all use the same RPC calls under the hood. Mempool .space calls getblock. Your hardware wallet calls getrawtransaction. Lightning implementations call getblockchaininfo. Understanding this interface demystifies the entire Bitcoin software ecosystem. You're not learning an obscure tool. You're learning the common language all Bitcoin software speaks. The traceability you just demonstrated, following inputs backwards through history, makes Bitcoin supply independently auditable. No other monetary system offers this. You cannot trace a dollar bill from the Federal Reserve Press to your wallet. But every Bitcoin that will ever exist can be traced from its creation in a coin-based transaction to wherever it sits today. Run getxoutsetInfo on your node. It returns the total number of unspent outputs and the total Bitcoin supply your node has verified. Right now, that number sits just under 19.9 million of the 21 million cap. Nobody told you that. Your node computed it by validating every transaction since the Genesis block in January 2009. Now you know how to trace any one of those coins yourself.